Okay, for example 4, let's skip over points of inflection just for a moment and, streamlining the videos here and the notes, let's just find the highest point. And by the way, you dealt with highest points whenever you were maximizing functions, right? When you were optimizing functions. And how do you optimize anything? You have to take a derivative, right? You have to take a derivative. And, that's definitely going to help you out a lot. So here we go with, some definite boundaries. We need to be careful there because that can introduce endpoints. And that's something that you always check when you're optimizing. But look, let's take a dx dt. Let's take a derivative of x with respect to t. What do we get? Just 2t. What about the derivative of y with respect to t? That's going to be dy dt is 2 cosine of t. Okay? And when they're saying find the highest point on the curve, just like you did way back in first quarter, you could look at dy dx, because way back then, what you really did is you said, where is my derivative going to equal 0? And we could definitely take a peek at that. And, I think as you're beginning to trace this out, you hopefully are going to notice that this thing could equal 0, and we have a definite t constraint here, some restrictions on t. We're only going to be going between 0 and pi. But where could the numerator equal 0? Cosine is 0. For which angles do you think? Pi over 2. We'd say, well, at pi over 2, of course, our derivative would be 0. And, obviously at pi itself, cosine of pi is -1. Cosine of 0 would be a 1. You might also be interested in looking at where your denominator could be 0. That's where your derivative would be undefined, mind you. And, where your derivative is undefined, we saw corners and cusps, right? And that's something else to consider. So you could say, well, what if 2t was equal to 0? Then we'd get t is equal to 0 itself. Now, how did we proceed way back in September? We did a number line, didn't we? And we said, you know what? This is great. We could put a little number line right here and say, well, clearly we're going from 0. We can only get as big as pi. And over here is pi over 2. And we would take sample t values. Like we might test t equals pi over 4. By the way, you're free to choose whatever t value you would like. And then between pi over 2 and pi, totally up to you what you'd like to test. 3 pi over 4 would be great. And, I just saw pi over 4 as the middle value between 0 and pi over 2. You're free to choose anything there. If you would rather have done pi over 6, it's totally up to you. But look, dy dx, if you think about it, guys, dy dx, the 2's would cancel out, and you're saying, wow, I've really got cosine of t all over t. And if I plug in pi over 4, guys, cosine of pi over 4, isn't that root 2 over 2? Guys, most importantly, it's positive. That's what I want you to hang on to. It's positive. And then down below at t equaling pi over 4, that's positive. What you're seeing is y prime is positive there. That means y itself, do you guys remember making these number lines? You're increasing. The function y with respect to x would be going upwards. And then you'd say, well, let's plug in 3 pi over 4. Well, plug it into this derivative right here, and let's see what's happening. What's the cosine of 3 pi over 4? It's negative radical 2 over 2. And down below, it's still a positive 3 pi over 4. So you'd say, hey, that's going to have to be something negative. Or we could even connect that. What kind of an extrema does it look like we have? A maximum. So that's where we would expect to be at the highest location on our curve, right? So we're going to say that it looks like we have from this guideline, it looks like we're going to have an absolute max at t equals pi over 2. Now, you might think, can you say that? Just from this information on the number line. You're going up and up and up, then you come down. Is there any way an end point could be higher than that point in the middle? No way. Do you know what? Let me tell you what can happen. I want to warn you. So many times kids cringe when they get a test back because they'll say, oh, what's the highest point? The highest point is t equals pi over 2, Mr. Dobner. Did you just name a point? No. You got to plug it in. You got to plug it in. So please watch out. You could say, well, x would equal pi over 2 squared minus 5. Y would equal 2 times the sine of pi over 2. And, so x evidently is going to be this rather ugly pi squared over 4 minus 5. And, sine of pi over 2 is 1, so y would equal 2. The highest point, they're not even saying what's the highest y value. A lot of times in this unit, they're going to ask for ordered pairs. You could say the highest point would be right here. Okay? We doing all right? Yeah. Well, you could turn that into a decimal if you'd like, and that would be rewarded equally. That's good. Yeah, another question. Yes?
You don't justify it?
Well, if they were asking you to justify it, you could say that, because y prime changes from positive to negative, there is a relative max at t equals pi over 2. You could say the endpoints are lower from the diagram if they're asking you to really put all that detail in. Therefore, we have an absolute max at t equals pi over 2. Okay? So that would be, the justification. You'd want to talk about a change in the sign of the derivative. Okay? All right, guys. Let's take a look at this next little problem here. This is so great. I love talking about example 5 because sometimes that seems to be an insane question for 5A. 5A, my word. Kids look at that. They're saying, did you just make a typo? You said there are 2 tangents at a given point? 2 tangents? Sometimes kids will understandably say, I just don't see how that's even possible. Guys, if you're talking about, 2 tangent line slopes, what do we have to take? A derivative, right? We need to take a derivative. Help me out. What's dx dt? That's 2t. And what's dy dt? 3t squared minus 3. And then kids will correctly say, now dy dx is dy dt all over dx dt. And here is where, guys, sometimes kids will say, this just sounds to be insane. Here's my formula for the derivative. You're telling me there are 2 tangents? You're telling me that there are 2 tangents there? And maybe we should even find the tangent line slopes? Sometimes kids look at that and they'll say, wait a minute, Mr. Dobner, that's crazy. How about we graph it? Maybe that will help you a little bit. Let's maybe do that. Of course, you've got this right here. That can be a huge help. But let's maybe type in t squared. And down here, I'll clear that up. We'll say t to the 3rd minus 3t And again, graphing this thing really depends on your window. Notice I made some changes. I went from -4 to 4. Sometimes kids will be like, oh, maybe I'll just go with 0. You'd say, well, maybe, if you'd want. Look, if you went from 0 to 4 or 0 to 2 pi, I think so very often 2 pi is that default. You know, you hit graph and kids will say, you're telling me that there are 2 tangent lines at 3, 0? Kids will say, that's nuts. Well, wait a minute. Put in -2 pi. Now graph it. Oh my gosh, would you look at that thing. Parametrics open up the door, guys, to looking at some crazy looking curves. I mean, you look at that thing, that's amazing. Look, I'm going to get up. Would you agree that at 3, 0, you might be looking at this tangent line that I'm holding the stick up to, or this one? Wow. There are 2 tangent lines. So all of a sudden, kids will scratch their heads for a minute and they'll say, how do you find those slopes? Well, what you need to do is start to think in a backwards direction. Look, I'm going to do a little bit of work here. We've got 3, 0. We've got x is equal to t squared. We've got y is equal to t cubed minus 3t. You're saying x is equal to 3 and y is equal to 0. Wow. Look at that. If you plug in the x-coordinate into the parametric equation, you could solve for t. How many t values will you get? 2 of them plus or minus the square root of 3. Yikes. Wow. And all of a sudden, kids look over here and they'll correctly say, now wait a minute, Mr. Dobner, if you factor out a t, won't you get t equals 0 and also t squared minus 3 equals 0? I think we just saw that t is equal to plus or minus 3. But sometimes kids will say, look, you solved that second equation, you also get t equals 0. And sometimes kids are a little upset about that. And they'll say, so are there 3 tangent line points at that point? Are there 3 tangent slopes? No. 0, plug in 0 in for t, and look, x would be 0 squared. You'd be at x equals 0. You see what's happening? So really, yeah, if you just were looking at y, you'd be in trouble. Because here are the 2 t values that are getting you into some information. Hey, check this out. Maybe this is cool for you to take a look at. Hit trace real quickly and type in the square root of 3. And it says, oh, you mean right there at 3, 0? Type in negative square root of 3. And it lands you at the same place. Do you see that? Isn't that nice? So what's happening, guys, is you're going to plug in t equals the positive square root of 3 and the negative square root of 3 into this form. Now, look, if you want to get some help, you could work this out by hand. You could also work it out with the calculator. But look, if I were to plug in radical 3 squared is 3. 3 times 3 is 9. 9 minus 3 is 6. And then down below, I'd have 2 times the square root of 3. If I plugged in negative radical 3, I would get pretty much the same thing. Negative radical 3 squared is 3. 3 times 3 is 9. 9 minus 3 is 6. But down below, I'd have 2 times negative root 3. My 2 tangent line slopes are 3 over root 3 or negative 3 over root 3, bringing that negative up. Everybody see that? So here are your 2 tangent line slopes that you could be taking a look at.